the second problem 3. All right, our goal here is to find w prime of 20. So first we got to find w prime of v in this problem. And this is a problem about wind chill, and we're plugging in like the speed of the wind and getting what the temperature would be lowered to based on the speed of the wind. So w prime of v would just be, well, the derivative of 55.6 is just 0. So we get negative 22.1 times, pull the power down, 0.16 times v to the negative 0.84. Cool. I can simplify this derivative very easily, and I can get negative 3.536. By simplify, I mean plug it into my calculator and get the answer. Great. Now I need to find w prime of 20. So I just plug in 20 here. And should you do that, you get negative 0.286. Now we got to talk about the degrees of this thing. So this is where things get a little weird. So W is in degrees because it's like our wind chill temperature after the miles per hour are accounted for. But our unit that's changing the problem is in miles per hour. So this is actually negative 0.286 degrees Fahrenheit per mile per hour. Pretty weird degrees because we have per and per, or pretty weird units rather. Now we're not done. We need to explain the meaning of w prime of 20 in terms of the wind chill. So usually this means write a sentence. So the temperature, I should write the wind chill temperature is decreasing by 0.286 degrees per mile per hour at v equals 20 miles per hour. This is absolutely the best explanation of what that is. Well, I mean, you might be able to phrase it better than me, but I mean, this has all the necessary information in it. And we're done. That's A. B is going to require a little bit more calculator magic. So it says, find the average rate of change of W over the interval 5 to 60. So the first thing we need to do is just plug in 5 and 60 into the W of V equation. And so I did that, and W of 60, I got 13.503, or 0503. And W of 5, again, I'm just plugging 5 in for V in that equation in the problem that I'm given, is 27.0091. So hopefully it makes sense to you that the faster the wind's blowing, the colder it is. So it's like 13 degrees here, whereas when the wind's going 5 miles an hour, it's 27 degrees. All right. Our next idea is, well, we're finding average rate of change, so we're going to do y2 minus y1, 13.0503. Whoops, too many zeros. Minus 27.0091 over 60 minus 5. So this is the wind chill at 60 minus the wind chill at 5 over 60 minus 5. If you plug this into your calculator, you get negative 0.253796, or if you round it 3 decimal places, which is the AP way, you get negative 0.254. Our units again in degrees per miles per hour. But we're not done. That's just the first sentence. Now we need to find the value of V at which the instantaneous rate of change of W is equal to the average rate of change, which is we just found. So all we want to do is find where our derivative, which is negative 3.536 times V to the negative 0.84, is equal to negative 0.25. I kept my decimal places to solve for this, all that stuff. And this isn't that bad to solve. I actually graphed these two things and found their intersection because that's my favorite way of going through these. But you could do this algebraically and it'd work out the same way. When you do this, if you graph it, you get that v is equal to 23.011. And our units here, because it's v, velocity, would be miles per hour. So at 23 miles per hour, we reach our average velocity using average rate of change over on that interval. And that's it for this second question.